So in this video, we're going to prove what we're going to call our theorem 5. And the theorem 5 states that x plus y enclosed within the parentheses plus z is equal to x plus y plus z enclosed within the parentheses. Now this is also commonly called the associative law of addition. This is the associative law of addition here, right? So before we begin, let me give you an intuition behind it. In the previous video, we have seen the intuition behind this statement. Now let me again revisit it. Now let's assume that x here is equal to 2, and then y is equal to 3, and z is equal to, and let's see what it translates to. So we can write it like this. We can write it like this: 1 plus 1 for 2 plus 3 is, if you decompose it into its successors, then 3 is just 1 plus 1 plus 1. This is what 3 is. And then 4 is basically 4 successions. And then for this is for this part. This part we have written it like this. Now for the right hand side, what can I write? I can write for the right hand side, which is 2 plus 3 plus 4. I can write it in this way. See, and now the part where we have to see that whether they correspond to each other. Now we can see that all of these parts, they correspond to each other, and then we can see intuitively that the right hand side is in fact equal to the left hand side. But this is the intuition behind it. This is not the proof. This is not the proof. See, this is only the intuition. In order to prove it, we will have to use induction, right? And what did we do in induction? We first proved it that the statement was true for 1, and then we proved that whenever it is true for x, this is what we have to show, that whenever it is was true for x, it was also true for x prime. So if we have we have proved, or if we have shown that these two statements they hold, then by axiom 5 we can say that the statement that we are trying to prove is true for natural numbers. This was our axiom 5 of natural numbers. Now to the proof. But before we start with the proof, let me first uh, remind you what the properties of additions that we proved were. The first property was x plus 1 was equal to x prime, and the second property was x plus y prime was equal to x plus y whole prime, right? And the first part of the proof is going to be the proof where we consider z to be 1. And writing z to be 1, can I write it like that? This part of the statement, can I write it like that? X plus y plus 1. Yes, I can, because we have assumed z to be equal to 1 here. Now, having written this, can I write x plus y whole prime? I think I can, because this follows directly from the first property of addition. Now, can I expand this and write x plus? Can I write it like this? That I think I can, because this follows directly from the second property. And now, can I expand this y prime here and by writing it as x plus y plus 1? I can, because this directly follows from 1 here. And so if you closely follow what I've done here, I have expanded this to this, and hence I have shown that both of these are equal to each other. And so we can write that x plus y plus z is equal to x plus y plus z enclosed within the parentheses are equal to each other, or it holds when z is equal to 1. Now this is the first part. In the second part, we are going to show that uh, this is true whenever this is true for x prime whenever it is z prime whenever it is true for z. Now let's move on to the second part. In second part, we are going to assume that x plus y whole enclosed within the parentheses plus z is equal to x plus y plus z enclosed within the parentheses holds, right? It is true for x, right? Now again, if I write it here, the second property of addition, the two properties of addition that we proved, what were those? It was that the first one was x plus 1 was equal to x prime. The second one was x plus y prime was equal to x plus y whole prime. Now can I write it like that, x plus y plus z prime? Now I'm going to expand it, and then I'm going to see how it goes and how does it expand. And to expand it, I can write it like that: x plus y plus z, and this is the prime of it enclosed within the parentheses. I can write it like that because this follows directly from 2, right? And now can I expand the inside of it in such a way as to write it as x plus y plus z whole prime? I think I can, because if you remember that we have assumed that this part holds, right? And so this follows directly from this statement. This follows directly from this statement. And so I've expanded the inside of this parentheses here to this side, right? And now we are going to do some uh, mathematical gymnastics again to prove the case. And now can I write it like this? I can write it by virtue of the second property. And again, expanding this part from the second property, I can also write it as such that x plus y plus z prime, because these are equal to each other, right? And so if you follow closely again, I have expanded this to this, and this is actually what we wanted to prove, right? We wanted to prove that this holds whenever this holds for z, and so these two are also equal to each other. And so I have proved that x plus y plus z is equal to x plus y plus z enclosed within the parentheses holds for z prime whenever it holds for z. And so x plus y enclosed within the parentheses plus z is equal to x plus y plus z enclosed within the parentheses is true by axiom 5. And what was our axiom 5? It was our axiom of induction. And so we have completed the proof, and we are going to make our box here, right? And so this is true for, actually this is true for natural numbers, right? Now in the end, I want to you to appreciate the proof. First we have proved it for the case where z was equal to 1, and then we have proved it for the case whenever it was true for z, it was also true for z prime. And then at the end, by virtue of axiom 5, we have proved the whole statement or the whole theorem.